Hey everyone, this is Matt with Learn Everything About Design. In today's video, we are going to be going through assembly joints as well as constrained components. We're going to talk about context sets, motion links, motion studies. We're going to try to cover all of this stuff in this video. If you are trying to follow along, go to the description of the video and you can download the assembly joints and constraints dataset. This is a hybrid design, which means that anybody on a hobby license, the functionality should be exactly the same. The EDU and commercial license does have a bit more flexibility when it comes to some of this functionality, but the tools should still all work the same for everybody. You're just going to be missing out on some functionality like bill of materials, things like that. What we want to do today is we want to first cover joints. We're going to go through joints and as-built joints, and then we're going to talk about constrained components before moving into things like joint origins, driving joints, motion links, motion studies, and so on. I will try to put chapters at the bottom for everything. So if you want to jump ahead to a specific joint or constrained component type, you can do that. If you are looking for more content, we do have absolute beginner series of content for assemblies. I'll leave a link to our website in the description of the video as well. All right, so to get started, the first thing we're going to do is make sure that we show the joints component. It's got several different components underneath the joint base, which is the piece that has all these little features on it. And then it's got a couple of knobs, the ball, it's got a spacer, a slot knob, and this block. So we're going to walk through the process of what sort of each of the joint types is. But first, if you don't know, joints and as-built joints, essentially the functionality is the same. The difference here is that as-built joints make use of the current component location, which we're going to do when we get to the slider because it was designed in place. Whereas the joint functionality, we have to make a selection first on the points that are going to be put together. It's called a joint origin. Now, the main function of a joint is to restrict the degrees of freedom, or essentially define the degrees of freedom with one operation. When we get to constrained components, we are selectively removing degrees of freedom one at a time. So that is essentially the difference. You can actually duplicate or replicate a lot of the same functionality with both, but there are some general rules, some reasons why I would pick one over the other. I typically go for a joint if I'm looking at creating motion between components, and I'll go with constrained component if I'm looking at locking two things together relative to each other and their geometry. So let's first get started with joint, and the first one is going to be rigid. So this red piece right here, which is our knob, is free to float around. Fusion keeps track of the coordinate system of each component. So if I look at the origin, you can see that it's moving with that component. The origin is how Fusion tracks the location, orientation, position of each component. We can revert its position or we can capture it, which will add a feature in the timeline. But in reality, when we're building an assembly, we want to put them together how they would be in the real world. And so a lot of times what we do is we create joints that will allow us to define the degrees of freedom. So the first joint we're going to take a look at is going to be the rigid joint. Now, the first thing we generally need to do is select the positions where we want the things to sort of join together. So on the boss here, we're going to hover over the edge and note that the little coordinate system gnomon snaps to the center. We'll left click there. And then for the inside of this red piece, I'm going to hold down Control when I'm over the center. That will lock its focus and I can move up and down pretty easily. If I don't hold down Control, it's going to jump all over the place. You can still get to that bottom edge. It's just a little bit harder to do. And then I'm going to left click. Notice that it moved the base over. Now this is only temporary. This depends on the order in which you click or select the things. Now the reason this is important is because when we're animating a joint or when it's looking at the joint motion, it's going to only take a look at the two components selected and not respect anything else. This piece is pinned in place. It's locked down to the top level component. So in reality, it shouldn't move, but it doesn't know that. It doesn't care. The motion type is set on the second tab. This is where it's rigid by default, and we're going to say OK. Now, notice in this case that it actually overlaps the solid geometry of the text I have here. It doesn't care because it said we clicked the two positions and it's going to put it exactly where I told it to put it. All right, so we're going to repeat this process. The shortcut is J for joint, so if you want to use shortcuts, you can do that. This time I'm going to select the blue object. I'm going to hold down Control and go to that bottom center. And then I'm going to come here to this position. Notice the blue one now moves toward it. We're going to go to our motion type, and we're going to set this to Revolute. Now, Revolute is a single degree of rotation. Now, if you want to preview the motion again, you can hit the play button. You can see it rotate around. Again, it doesn't care about the text. It's just going to go through it. For our example, that doesn't matter. Obviously, in the real world, it wouldn't be able to rotate through that. So we're going to say OK. And now, when we try to move the red one, nothing happens. When we try to move the blue one, it's free to rotate. You'll notice there's a little icon on the screen. And if let's try to hover over that so you can see it. It's not going to really get any better. If you double click on it, it'll drive the joint. Let's see if I can get it. You can see it displays the degree there, and we can just freely rotate this piece. And when we're done, we can either capture its position or we can revert its position. All right, for the next one, the slider. This one was designed in place, so I'm going to use the as-built joint so we can see. The main difference here is note that there's no selection of position. I just need to pick the components, and then I need to pick the joint type. Now, in the case of slider, you'll notice that there's nothing happening in terms of previewing the motion, and I need to pick a direction that I want it to go. So I'm going to pick this vertical edge here. Notice that it's moving up and down along that axis. If I preview the motion, you can see that it's kind of moving up and down. And notice that it's going through the solid geometry. We can control that by enabling what's called joint limits. Now, when we select the joint limits, we can lock a minimum and maximum value. For example, we could say we only want it to go up 20, and then it's going to stop at the bottom and only move up in that 20 millimeter amount. We'll say OK, and now I can freely move this piece up and down. Now, again, in reality, this piece would be free to rotate, so there are other joints that would be a better option. But sometimes the slider is a joint that we use to replicate 1 degree of translation. So I'm going to go into my relationships folder. I'm going to expand the joints. And for the slider, I'm going to right click and notice that I've got some options. I can lock the motion. I can suppress it. I can animate the joint, which will let me play back through it. But what I want to do in this case is actually delete it. So I'm going to right click and delete it. Now we're going to go back to as-built joints. We're going to go to our options here, and I'm going to select cylindrical. Once again, same selection process. And this time it needs me to select an axis of rotation and then an axis of translation. So I'll select just a cylindrical edge. And notice how it's kind of moving up in sort of some crazy orientation. If you make an improper snap selection, you can always go back and try again. And you can see there now that I selected the center, it's moving properly. Notice now for my joint limits, I've got a joint limit for rotation and a joint limit for the slide or the translation. So I'm going to limit the slide or the translation. Again, we'll go 0 to 20 and we'll say OK. So now I can move this up and down and it's free to rotate. It's a little bit more realistic. This is how the real parts would behave. Now the benefit here of using something like a joint is that it's much easier for Fusion to calculate over using something called contact sets. We'll take a look at contact sets a little bit later. Just note that these oftentimes are needed for more complex motion that you can't easily describe with these joints. All right, next we're going to go to joint. We're going to select the bottom portion of this green knob, and then we're going to select our slot. I'm going to go ahead and just put it here. Don't worry about that selection just yet because we want to go to the motion. We want to set this as pin and slot. Notice now that it's moving back and forth. We can change the limits for the rotation as well as the slide, setting our minimum and maximum. Now, this can be a little bit tricky, so what I find is a little bit easier to do. Oftentimes, I'll come to the bottom and I'll use the on-screen manipulators to determine where the minimum and maximum values are. Then I'll hit play and allow it to sort of bounce back in between those. Once again, this is a case where historically we would use something like a contact set, something that would physically stop it. But now we can use those limits that allow us to stop it at either position. Again, don't worry about the text, it's just there so that you can see. But this allows us to rotate and move along that slot. There are limitations to this. This works really well in these sort of straight slot scenarios. Once they get a bit more complex, something like a cam follower, for example, it's really not going to be the right option. All right, next one that we have, we're going to go to Joint. I'm going to go to the Motion tab first to make this a little bit easier. We're going to go to Planar. And so all the joints we've looked at so far, rigid locks everything down, Revolute 1 degree of rotation, the slider 1 degree of translation. Then we went to our cylindrical, which is 1 degree of rotation, 1 of translation. Pin slot, 1 degree of rotation and translation, but different axes. And now with the planar, what we're going to be doing is having something that can move and rotate in plane. So what I'm going to do is I'm going to select the bottom of this face, and I'm going to select inside of here, and I'm going to say OK, but I just want to make a quick note here. It can rotate, it can slide in one direction, and it can slide in another direction. So we're going to say OK. And basically, this allows me to move this block around. Now, again, it's not really taking a look at any solid geometry. So if we want to take a look at solid geometry, we have to enable contact sets. So I'm going to go ahead and enable contact sets. I'm going to come up here, and there's all body contact and there's no contact. But if you right click on this, we can create a specific contact set between two things. What this allows me to do now is to sort of pull this block around, and it will physically stop when it gets into the corners. Notice that it's stopping when it hits the text. And you can even get it, depending on where you grab and move, you can even get objects to rotate and sort of spin around. But this one actually takes a look at the solid geometry. But keep in mind, it is processor intensive, so it will take a lot of computation to make that happen. I'm going to go ahead and revert the position. You can also come up to your contact sets, and you can delete or suppress or disable them if you need to free up some memory. All right, the last joint that we have is the ball joint. Now this one takes a look at 3 degrees of 3 degrees of rotation. Sorry. So motion, ball, and then we're going to put this ball, which we need the cylindrical center of, and then this socket here, again the cylindrical center of. If we go to motion, we can hit play, and you can see it kind of rotates around. So if you grab onto this, it should be free to rotate about each independent axis based on its location. So if you think about an origin and you've got the X, the Y, and the Z axes, you can have it rotate independently around each of those. Sometimes this is easier to see by going down and actually using the drive joints, because this will give you 3 independent rotations. So you can see here, go that direction. This one is going to be essentially the same. And then this one's going to rotate that way. And then now it twists about a different axis. You can see this one going here. I'm going to hit OK, and I'm going to revert the position. And so those are all of our joints. Now, there are some nuances in joints I didn't really talk about. So I'm going to hop back into the joint menu real quick. And that is going to be the origin modes that we have available. In most cases, simple, which means you're snapping to a specific point, is going to be the best option. There are other ones, such as between two faces or two edge intersections. So these can be helpful, especially if you have got a rounded corner and you need to lock a joint or lock a component into a specific location. There are some limitations with between two faces. We're going to talk about that later. I've got an example for that one. But just keep in mind that the simple origin mode is the one that's most commonly used. All right, now that we've taken a look at joints, I'm going to go ahead and hide the joints, and I'm going to show the constrain components. Now, this is the exact same example. I wanted to talk about this first before we get into a specific constraint example, because I think it's important that we identify the differences in how these tools work. So assemble and constrain component, again, what we're doing is we're locking the degrees of freedom one at a time. There are 4 different types. We've got an align option, we've got an angle option, between two faces or center, and then a tangent. Now this tangent is actually exactly the same as tangent relationships. It's just inside of this dialog. All right, so first let's take a look at this red one here. Now with a joint, a rigid joint specifically, we only had one selection to lock it in place. With constrained components, we need to select the cylindrical center, and we're going to select this. And we'll hit the plus icon. You can either do it over here in the dialog, or there's a plus icon here. Then we need the bottom of the component. Now, one thing to note is the first component you select will need to have a selection with every other constraint that you're adding. And so keep in mind the first one is really important in this. We'll select here, and that's two constraints. So what we did was we locked down its vertical orientation. It can't slide up and down. And we locked its position based on the cylindrical center. But it's still free to rotate because nothing is locking this orientation down. And in order to lock that down, we would really need to have some additional reference. Right now, we don't have any straight edges that could lock it down. We don't really have a good way to do that. And so for a component like this, something like a rigid joint is really the best option. So let's go ahead and try that again. Constrain components. Again, this time we'll use this yellow one. We'll hit plus. We're going to select the bottom face. Hit plus. And you can see now on this third one, we have to decide how we're going to lock this in place. So I'm going to select the angle option. And I'm going to select this face here, and I'll select this one here, and we can lock it in at 0 degrees and say, okay. This will positively lock its position because it is basically it's stuck down to the floor or the top of this part. It's cylindrically or concentrically located. And now we put an angle between these two. All right, let's take a look at one more example here. Again, constrain components. What I'm going to do is I'm going to put the bottom of this on the top of that. I'm going to say okay. Now, this is free to move around. Again, it's not looking at solid contact, so it can go through walls, but this is essentially like the planar joint. We could theoretically rotate this if we want. It's just simply saying that this face here and the bottom face of that green block are together. Now, constraint components can also be used for something similar to a ball joint. So the face-face contact, in this case, because they're exactly the same, would produce the same result. I'm going to undo that, and I'm going to do this again using the tangent relationship and making those tangent, flipping the direction, saying okay. Again, is going to give me a very similar result to the ball joint. Now, the reason, the thing that happens here is we've got less control with constrained components because we can't drive joints, we can't animate joints, or rather we can't animate constraints like we can with joints. That's where things like a motion study really make a big difference because we need joints for that, at least currently when I'm filming this at the beginning of May 2026. And again, we've got this tangent option, which allows us to take things like cylindrical parts, and we can have them always follow the side of a part. So if we view this from the top, might be a bit easier. So you can see this part can sort of rotate around and move back and forth, but it's always going to remain tangent to that face. And so these are ways that we can create joint type motion, but again, they're not constrained. Their degrees of freedom aren't really locked down in the same way. What we typically use these constraints for is when we're trying to put together components that don't always need joints. And think about things like putting hardware together that are stacked up, putting bearings inside of a housing, potentially putting complex shapes like plastic parts together. These are areas where constrained components really work. There are still cases, again, where you would decide to go one way or the other, and the implications really come down to how you want to drive and control the motion. I generally will go to using things like a joint when I have mechanical motion, and I'll use constrained components when I'm trying to lock that motion down. And so we're going to look at this example here with the constraint example, and I'm going to do it with joints, and then we're going to do it with constrained components, and then hopefully you can make your own decision. All right, so the first thing that we want to do is I'm going to go to Assemble and Joint, and we're going to set the motion to Revolute. And I'm going to start by using the Between Two Faces option. Now, the reason I'm using Between Two Faces is because this allows me to get a center location on that component. And component 2, I'm going to use Between Two Faces. I didn't complete the selection. I'm going to go back in just a second. They both need a snap point. And so the snap point is going to be the axis of rotation. I'll go back to this one, axis of rotation, and then I'm going to say OK. And so now this gives me that hinge position. And the between two faces, if we view this from the top, is because the brackets themselves don't share a face. So the faces wouldn't line up. They're sort of free to move back and forth. You oftentimes will have this when you're dealing with physical components. There's tolerances involved, there are gaps that are needed, especially with things like door hinges. These are going to have a gap between them. So we don't generally put two faces next to each other. The other thing that we have, so for this pin, for example, the pin itself can be rigid because all the motion is coming from these brackets. So we could use either constrained components or we could use a rigid joint. Now in this case, I'm going to go ahead and use constrained components. This is a good use case for it. We'll put the pin in that cylindrical face. We'll hit plus. We'll select the underside of the face and the outside of the sheet metal component. Snap them together. It doesn't matter if the pin rotates. It doesn't really have any impact on the design. And the hinge still freely rotates because its rotation is based on that joint between the two components. And so this is a use case where you could decide to use both joints and constrained components, and either would work fine. All right, let's take a look at another example, and this is bracket bodies and bracket components. And what I mean by this, I'm going to go ahead and expand these. The bracket bodies has two bodies inside of a single component. Now, the reason this is important is because if we go to use things like a joint, and we say between two faces, if the bodies are part of the same component, this will work just fine. However, if we instead show bracket components and we do the exact same thing, say between two faces, notice one of the components is changed, the opacity changed. And that's because the bodies don't belong to the same component. And so a lot of times when we've got brackets or mounts for things like pneumatic cylinders, most of the time when you import them, they're going to be all bodies in a single part, and you can get away with using the between two faces in a joint. But realistically, when you purchase these components, oftentimes they're independent. And so what you need to do is come to your assemble tools and create what's called a joint origin. When you select joint origin between two faces, you can select two planar faces that are independent, belong to two different components, and you can still create a joint origin. So this means if we come in to create a joint, instead of using between two faces, what we can do is select the joint origin as our location. And so this is very helpful as long as the two components are tied together or locked together in some way. You can do this by creating a rigid joint, by pinning them together depending on how you want them to move. Using the option to create a rigid group can also be very helpful. And the reason for this is because rigid groups allow the selection of more than two components, where a joint only allows you to select two. There's an include child components, which means that I can select the parent. It will automatically select all the children components in there. And the reason that that helps us is because now if we've got a component with a bunch of hardware, for example, let's say you've got a wheel that has a bead lock on it and you've got dozens of bolts on it. Those bolts are all going to be fixed to that component, and so using a rigid group instead of creating a joint for each one can be a good option. There is a sneaky little option in here called duplicate with joints. Note that this only works if you've got a joint, not an as-built joint. It can't make use of component locations. You can duplicate with joints if you use the manual joint option. All right, so there's a couple of other things that we want to talk about here. Those are going to be the motion links and motion studies, because we've already talked about contact sets, we've already used drive joints, so those are really the last two things we have left. So I'm going to use this option, or I'm going to change the joint for this block. And so what I want to do is go into my joints component, I'm going to go to this planar joint, and I'm just going to right click and delete it. Now the reason for that is because I want to add a different joint that's more reminiscent of, say, a control, like a slider. And so the slide joint is going to be between this block. Let's go ahead and I'll do it over here. Select the bottom here, and we'll select the bottom here, and we'll say OK. And so now this is free to slide back and forth along this edge. Think about it like a joystick or some sort of slider control. Now, the reason I want to do this is because using something like a motion link allows us to connect two joints together. So for example, it could be a slider or a linear translation with a Revolute joint. And so the reason that this is helpful is because now as we slide this, it's going to rotate another joint. I'm going to hit Control Z to undo, and we're going to go back to Motion Link. This can also be linked to other types of joints, but keep in mind that we need to pick whether we're controlling the rotation or in this case the slide. This is important because some types of joints like ball joints, pin slot, slider, and I'm sorry, in this case, the cylindrical one, they have 2 degrees of freedom that we're controlling, a rotation and a translation. Also, any joint limits that we have applied, so for example, this one can only move 20 millimeters, it's also going to affect other joints like the slider joint because this one can't move any further than that because they're now linked. So this is a really helpful tool. It works well for things like belts and pulley systems, rack and pinion systems, things that we can't really connect with chains or belts or hydraulics in some cases. So you can use things like a lever, and you can control the piston motion on a pneumatic cylinder, or you can control steering input on a rack when you've got a rotation or revolute input. So these are all pretty helpful. The other thing that we want to talk about, or really the last thing here, is something that's called a motion study. Now, this doesn't get used very often, but this is something that can be kind of handy. For example, when you've got a motion study, typically what you do is you select a joint, and then on the diagram here, you pick a point and you determine the movement of that joint, let's say 360 degrees. So now if I play through this, I'm going to turn the speed way down, but if I play through this, you can see that it's rotating that joint. Now you can select other joints as well. So for example, the slider joint here, notice that it opens up translation and rotation. So let's say here, we want to move this to, let's say 20 millimeters. That's its max extent. Because of our motion link, it's going to move everything. I'm going to go ahead and loop this through and play it. So you can see it's moving it up. It's moving this block because of the motion link. The Revolute one is rotating. So where this really comes in handy is if you have a mechanical system and you want to take a look at, say, steering input. You want the wheels to move left to right. A lot of times when you've got joints that replicate complex mechanical systems, a suspension system, for example, is going to have suspension travel. You're going to compress a shock. You're also going to have rotation for the steering. A lot of times when we just manually move those things, what ends up happening is more joints start moving. We end up getting into some funky situations where joint calculations just aren't working. So using a motion study can be a great way to just drive a single joint. And again, you can double click on a joint and you can drive it this way. You can kind of manually decide what you want to do. You can also select a joint in here and you can edit the joint. If you want to go back and change its limits, you can drive it from here, which is the same thing as double clicking. You can animate joint, which will take a look at just at one joint, or you can do an animate of the joint relationship. So animate joint, for example, doesn't make use of the motion link that we have, but if I use the animate joint relationships, now it makes use of that motion link. And so it'll respect everything else that's going on inside of the assembly. So I know that was a lot. We covered a lot in, I guess this is about 30 minutes, but there are probably a dozen different things that will come up when you try to use joints and constraints or constraint components in your own assemblies. Just try to remember, at least at a basic level, my rule is when I have mechanical motion, I oftentimes will go to a joint. And when I'm locking components together, I'm taking away degrees of freedom. Like if you assemble, let's say the top of a remote control housing to the bottom of it. A lot of times you want to lock those things in place. You can do that with a joint, like a rigid joint, or you can selectively lock down degrees of freedom using constrained components. There are going to be use cases where one makes more sense over the other, but really all you can do is play around with them, figure out what works best for you, and then ask questions. Now, once again, if you are just learning, we do have assembly and design courses on learneverythingaboutdesign.com. We don't go through all the joints like we did here. We go through basic examples like putting together a radial engine, putting together flight pedals and joysticks and things like that. So we look at those various different use cases and how to build them and put them together. So if you want some more content and you're looking for something else, go ahead and check out the site. I'll leave a link in the description below. But if you have any questions or comments or want to see more, please let me know. As always, thanks for watching, and we'll see you in the next one.